Question 7.43 says draw a plausible mechanism for each of the following transformations. So if I took a look at the first one, I'm starting with a tertiary alcohol and treating that with HBr. Therefore, I'm going to get a substitution reaction, and it's going to proceed via an SN1 mechanism. So the first step is going to be converting that poor leaving group, hydroxyl, into a very good or excellent leaving group, an oxonium. So let me draw that out. So we know that if we have three bonds to an oxygen in a lone pair, it has a positive charge. So now I have my oxonium, and now I get the loss of water. So I'll put minus H2O, and then what I end up with is a tertiary carbocation. And I've also produced bromide in the first step. So now my tertiary carbocation is open to nucleophilic attack by my bromide. There we go, like that. There's my last arrow. And the final compound is achiral, because the alpha carbon has two ethyl groups attached to it. So there we go. If we take a look at B, so let me change my colored pen here. So you can see that this carbon skeleton in D has rearranged, which tells us that this mechanism has proceeded by some kind of E1 process. So the first step is going to be protonation of the hydroxyl to convert it into a good leaving group. And since we're using sulfuric acid, which is a solution in water, and based on the leveling effect, the major component in sulfuric acid that's going to protonate our hydroxyl is going to be a molecule of hydronium. So if I draw the protonation step, so I'm going to draw my oxonium intermediate here. Just going to draw a condensed structure like that. Then the next step is going to be the loss of water. I'm just going to draw it kind of on an angle here because I'm running out of space. And then what we get is a secondary carbocation. But hopefully you can see that that secondary carbocation is prone to rearrangement, because if it undergoes a methyl shift like that, let me go back to my blue pen. If it undergoes the methyl shift, and I'll just draw my arrow in one direction because this is an irreversible process, then what I end up with is a tertiary carbocation. And also, even though I didn't have it drawn in there, we know that there is a proton on this carbon here that I've highlighted in green, and then that proton can be removed by a molecule of water. There we go. So I'm just going to draw a molecule of water like that, and that molecule of water can pull off that proton and give us our double bond. So there we go. And what you see is at the end of the reaction, not only do you get the desired product, but also in this step here, and I'll just use the green pen, in this last step here, you've regenerated H3O+, which is essentially a catalyst because it keeps getting recycled or reproduced over and over in the reaction mechanism.